let's talk about the ISS for a moment. The ISS is made of different materials. Kevlar, gold, glass of some kinds, I think polycarbonates, glass, metals, other things, Kevlar-like materials. We will look it up, and maybe I'll make a little list to go up and down here. But here's my point. In what we're told is low orbit, where the ISS glides around, in the direct light from the sun, you'd have radiant energy from the sun hitting the ISS. There is no atmosphere at that height to buffer the ISS. So there's nothing for the ISS to transfer the heat into it to dissipate some of that heat. And there's nothing around it to cool it down. So it can't, all it can do is radiate the heat out itself. So what happens is things that are in space, we're told, heat up to very high temperatures when they're in sunlight. And when they're not in sunlight, things are very, very cold in space. Because again, here on Earth, we have an atmosphere around us. And so when the sunlight warms the air, it takes a long time for that air to then cool down again. So overnight, we see it cooling down, but not enough. There's enough air that there's enough energy in the molecules and particles in the air that they just kind of keep shaking because of the heat energy until the next morning, when then there's more sunlight, which makes them shake even more, move around more, because then they get much hotter. And so even though we see it cooling down, we obviously don't see minus 170 degrees Celsius or minus 348 Fahrenheit that you see on, for example, the moon when it's on the dark side. Because there is no atmosphere around it to buffer it from the cold or to allow it to easily dissipate some of that heat into a cooler environment around it when it gets really hot, it would heat up to very high temperatures when it's on the day side of the Earth, and it would reach very cold temperatures when it's on the night side of the Earth. Much colder than what we experience here on the surface, because we have all these air particles around us that have been heated up by the daylight sun, and so all those particles are all moving around with all this energy that they've acquired from the sun, from the heat. And they slow down overnight, which is why it's cooler at night, but they don't actually get super cold, because there's still that leftover movement energy heat. The ISS is a completely different story. So why is this relevant? Because different materials have different melting temperatures and different freezing temperatures. As we know, metal expands very easily, very quickly at slightly increased levels of temperature. If you can't get your wine bottle open, you put it under hot water and the lid expands because it's made of metal, and then you can just easily open it up. And we use that in our day-to-day lives, so we understand that concept that most metals that we use for caps, they just, as soon as you put them under slightly hot water, they start to expand. So the metal on the ISS, when it's in direct sunlight and it's absorbing all this radiant heat, should start to expand. However, the different components of the ISS would expand at different rates. This is relevant when we think about, for example, someone told me I should have less cuts in my videos, but my camera keeps overheating and shutting itself off, and then I have to restart it. And that is one of the reasons why I use so much jump cuts in my videos. There are other reasons, but that's one of them. So, where was I? Different materials. The solar arrays. So the solar panels on the ISS, they have a metal outer casing, and then they have the solar panel materials itself in the center. So what would happen if the ISS truly was in space, in low Earth orbit, the metal around the solar panels, when it's in the daytime side of Earth, well, that metal would expand. And the solar panels themselves, because they're made of different materials, they would not expand as quickly and they would not expand as much necessarily. And so if the outer casing expands and the inner panels don't, they would fall out. They would fall out. Or they would warp, depending on how the framing is constructed. They would either expand out if they're solidly attached along the inner ridge or edge, if they're really well anchored. Then in order to expand and still be constrained to that inner edge, they would start warping. If they're not as well attached on the inner edge, if they're, let's say, just attached at the corners or what have you, then you would expect that they would expand outward and the solar panel would just fall right out into space. So either way, that framing would shift and bend and warp as it gets hot, and the solar array, the panel itself, would just break or fall out, shatter, it would be destroyed. And then when you go around to the dark side, because there isn't an atmosphere to make the temperature change more gradual, what would happen is the ISS would go from very 170 degrees Celsius to nearly minus 170 degrees Celsius. Kind of like that. Not quite like that, but kind of like that. In a very short amount of time, it would go from very hot, all melty hot, to, very cold, brittle cold. A lot of these metals get brittle when they get cold. Steel gets quite brittle. I just had a lot of wine. I'm really stressed because I want to make less of these jump cut edits in this video, and for some reason that's stressing me out, and so normally I am capable of talking at length, but today I'm having all these problems. It might also be because I'm really hot. Also, my lip gloss is being weird and I keep wanting to fix it. So, where was I? Yes, steel. Steel actually gets brittle when it gets cold. And so if you had any steel screws or components in any part of the ISS, then it would get really cold, slightly brittle, as it goes around the night side of the Earth. And then when it hits the day side again, the heat would be pretty immediate. And because that metal goes from being so cold to bathed in radiant heat, it would shatter.
When metals fail. Did you know that every block of metal has tons of microscopic voids inside it? And that these microscopic voids actually play a crucial role in failure. When a metal is stretched or loaded, these voids start to grow and link together until the metal fails.
It wouldn't have the ability to gradually warm up, and it would go from a very brittle state to trying to expand. It would just shatter. In the same way that if you take a Pyrex dish out of the oven and you put it in your sink full of cold water, it's an explosion of Pyrex. It actually happened to me the other day. And it would be the same thing, just an explosion. All the different pieces would go flying. So it simply doesn't make sense. And when you look at the ISS information on NASA's own website, you can see the images and you can see that there are different components. There's wiring, there's metal pieces, there's their Kevlar coating. The Kevlar coating doesn't coat all the different pieces, all the different components. So the idea that somehow there's something that protects it from the heat and the cold, well, that's just nonsense, because they obviously don't cover all the pieces. So whatever isn't covered would be expanding at a fast rate. Anything metal, anything plastic or any plasticize, those things would probably just start to melt. But anything metal would just start to expand. And then if it's connected to a part that is covered by their heat protection blanket, then that component would not expand. And it doesn't, valves would give, pieces would come unattached. It's just not, it doesn't make sense when you actually just sit down and think about the logistics of this machine in space. It just doesn't, it's just not logical. Having said that, I find it interesting that NASA does put all this information about the ISS on the website. And I was looking at the path that the ISS takes and the distance that it covers and the speed. This is another thing. One of the reasons that the ISS has this Kevlar-like shielding on it, they say, oh my goodness, it was tested by high-speed bullets to make sure that it would be safe against meteorite impact. Okay, first of all, bullets travel very, very slowly compared to meteorites in space. According to what we're told about space and about meteorites and everything that NASA tells us, everything that is space.com, everything that the entire industry revolving around space tells us about how things travel in space and the speed at which things travel in space. The idea that something that can protect you from a high-speed bullet will somehow be able to protect you from a meteorite is laughable. I can't believe that science-minded people buy into this. I can see if you just never really think about it and you just kind of accept and you're going along. But for science-minded people who are reading the website and taking in this information, how do you not reject this as, it's not ridiculous, it's beyond that, it's actually stupid. So I did a few calculations about a rough estimate of the speed at which a meteorite would be going, the average meteorite. We're told that 40 centimeters is the diameter. At least one 40 centimeter wide piece of meteorite falls into the Earth every day. So this means that in orbit around the Earth, coming in towards the Earth, there are these 40 centimeter wide chunks of space dust. Inevitably, that's going to strike the ISS. And this is why they put the Kevlar shielding on the ISS, except that they don't put the Kevlar shielding on the solar panels. And they don't put it everywhere on the ISS. And they don't put it on the windows of the ISS because they don't want to block the view. Now, if I did a calculation to see how much pressure per inch would be expended by a meteorite hitting the windows of the ISS, and I'll just insert that somewhere here. It's ridiculous. It's just not realistic. You wouldn't be able to have intact windows on the ISS when every single day you have these meteorites hitting it with this much power, this much pressure per square inch. Yeah. So hopefully I have helped you to think about the idea, the concept that maybe the ISS isn't really flying around above your head in space. However, if you're still really wedded to the idea, well then I have another issue for you. Because when you take from the NASA website the distance that the ISS is covering, it doesn't match the size of the Earth. In fact, the ISS numbers that were given in terms of the speed at which it's flying and the path that it travels on, it seems to suggest that the Earth is actually 195 miles bigger than it is. So if the world is a globe, then the ISS is somehow traveling around this globe. But the globe that the ISS is traveling around is 195 miles larger than the globe that you think you live on. And if the Earth is not a globe, then the land that NASA knows about is 195 miles larger than the land that you know about. I think that's interesting. How did I come to this? I'm going to look down to see my calculations. So the ISS speed is 17,500 miles per hour, and it circles the globe every 90 minutes. This is important as well. If the ISS is circling the globe every 90 minutes, as we're told, and as we're told, it sees, I don't know, I think they say 16 sunrises, sunsets every day, then it's going from extreme heat to extreme cold every 90 minutes, expanding and contracting every 90 minutes. If you have all these different components made from all these different materials, and they're expanding and contracting at different rates every 90 minutes, the idea that that would somehow last, survive, that it simply could not. If you still believe in the ISS, though, then you have to account for what is this 195 miles that NASA is sneakily telling you is there, but no one can account for. So you can use the diameter of the Earth, you can calculate the circumference of the Earth, and then you take the speed at which the ISS, we're told, is traveling at, and you take the 90 minutes at which it's going around the Earth, and using all these different data points, you can put this in a calculation, and you come out with the circumference of the circle around which the ISS is flying. And when you take into account the height at which we're told the ISS is flying, 240 miles above the Earth, there's a discrepancy of 195 miles. So, I leave you with that to make sense of for yourself.
Subscribe to my channel. I make a new video every now and then. Flatter, like it, give it a thumbs up, give it a thumbs up, like it, give it a thumbs up, give it a thumbs up. Or some more flatter, true conspiracy. Subscribe for more sparkle sounds. Share it with your friends. Conspiracy. Sparkle sounds. Princess dress up. The mental and blog. Sparkle sounds. Princess dress up. Or some more flatter.